Hi, welcome to Chem with Chem. In this session, we're working question number 6 from the January 2018 edition of the CXC CSEC Chemistry Paper 2. Oh, that's a mouthful, gets me all the time. If this is your first time to the channel, welcome. Please check out all the other materials that are here. Like if you find value, share with a friend, and if you have not subscribed, then consider doing so and hitting the bell so you'll be notified the moment new material is added. Let's see how quickly we can do this one without compromising quality, of course. Let's go. Part A of number 6. List 4 unique properties of water as it relates to the human body. We have to relate them to the human body. So we're not just listing 4 unique properties of water. Yes, water is unique, water is great, but we have to relate them to the human body. So the first one that we're going to give is the fact that it has relatively high melting and boiling point, and we'll see how that relates to the human body. Melting point is 0 degrees Celsius and 100 degrees Celsius. So at between zero and 100 degrees Celsius, water then would exist as a liquid. So at the optimum body temperature, water is a liquid, making it very useful for all the other functions that it carries out in the body or that it facilitates in the body. So it is a liquid at the body's optimum temperature, making it most useful. All right, and if you're able to put this in fewer words, all the better. So we're going to fit the other 3 in the space that we have left. So another property of water that and another unique property of water and how it relates to the human body. The first one that we've listed is related to all the others in a sense. So the second one that we will look at is the fact that it's a universal solvent. So it dissolves ionic and covalent substances. It dissolves minerals and food. So it allows for substances to be dissolved. So chemical reactions can take place within the cells. So food can be transported. So the body can rid itself of waste. So all of those things. Three, the third unique property, it has high specific heat capacity. It has high specific heat capacity, so this makes it hard for the temperature of the body so it can absorb a lot of heat without the temperature changing. So in a sense, we don't overheat. So it absorbs a lot of heat without changing temperature. So the body temp is kept constant. And 4, and as I said, if you can summarize, then all the better. I've been working on summarizing from high school. And the last one, it has a high heat of vaporization. And this is good because it helps to It helps the body to cool down. There's heat exchange taking place from evaporative cooling. So the body can cool down through sweating. And that would give us 4 marks. Water exists in liquid, solid, and gaseous state. Describe a laboratory test for water vapor. Okay, so we use cobalt 2 chloride paper. The presence of water vapor changes it from blue to pink. We could also use anhydrous copper 2 sulfate, which is white, and the presence of moisture, the presence of water, causes it to change from white to blue. That would give you your marks. Part C. In some Caribbean islands, calcium hydrogen carbonate causes temporary hardness in water. Definitely here. This can be treated by the use of washing soda, sodium carbonate. Write a balanced chemical equation including state symbols to show the removal of temporary hardness from water using this treatment. So we're going to just write the balanced equation straight up, and this is a good equation for you to practice to write your ionic equations from, but we're just going to get to the point and just do what is required of us. So calcium hydrogen carbonate is aqueous, it's soluble, so it's Ca bracket HCO3 bracket 2 aqueous plus washing soda Na2CO3 aqueous, and this will give us, this is a double decomposition reaction. This will give us, well, it could be called a precipitation reaction as well. It is both. It will give us calcium carbonate, and that is what will pretty much arrest the calcium ions, because if we're removing the ions that cause the hardness, if we remove the ions that cause the hardness, then it means that we're pretty much softening the water. So this will pretty much arrest the calcium ions because they're pretty much being removed. That's what's happening in the background. But we're not going to be breaking it down to look at the ionic equations. You can do that for practice. So, and then this will also give us sodium hydrogen carbonate. But yes, it's aqueous, and we would need 2 because we have two sodium in the Na2CO3 sodium carbonate. So this would be 2 right there, and that will do it. We are balanced. That is it. 3 marks. So when this happens, this is how the calcium ions are arrested or they are removed. And this is the last question, question D for 6 marks. Be not dismayed, it looks big. The first one was all of 4, this 6. It's fine, let's just break it down, literally. Pure water does not conduct electricity, but can be acidified using dilute sulfuric acid for this to occur. Predict the ions that will migrate to the anode and cathode during the electrolysis of dilute sulfuric acid, aka acidified water. Write a balanced chemical equation including state symbols for the electrolysis of dilute sulfuric acid, acidified water. All right, so before we look at the ions that will migrate to the anode or the cathode, let us look at the ions that are present. So we would have H plus, well, from the water that would have been acidified, and from the sulfuric acid itself, SO2 4 minus, we would also have OH minus, that's the hydroxide ions from the water. And yes, we have H plus again from the water. H plus, they're still identical, still H plus at the end of the day. So we have the cation we have here would be H plus, and the anions we have are sulfate ions and the hydroxide ions. So just a reminder, I normally put a sign beside the electrode so we don't put like charges together. So anode is positive. So the ions that would migrate to the anode would be the sulfate ion, the SO4 2 minus ions, and the hydroxide ions, OH minus ions, and these are aqueous. They're in the presence of water, aqueous coming from aqua. Now the ions that would migrate to the cathode, we only have one type of cation, one type of positive ion, so we only have H plus going there. Now the balanced equation for what is happening, all right, I'm going to put the balanced equation at the end. But to get the balanced equation, we're going to be looking at what is happening at each electrode. But we're just going to put the final thing at the end. Now, I've always advocated for us to use the correct convention when we're writing oxidation. Some books will show minus, whatever the species is minus, whatever the species is minus electrons, but that convention is incorrect. And this is a question that shows us why we use the convention that we use, or why this convention is to be used or is correct. So, all right, so let us look at what happens. Let us look at what happens at the anode and at the cathode. So I'm going to use blue so we can be guided. We know that we're just showing you the half equations, and then we're going to put the half equations together to give you the final balanced equation. So, of course, a little background at the anode. Well, a lot of answering is required in the background here because we have to decide which ions, which of the negative ions, which of these anions will be liberated or will be given the nod. So we'll have the electrochemical series for anions. We have carbonate, sulfate, nitrate, chloride, bromide, iodide, OH. So OH is lower in the reactivity series, which tells us that it requires less energy to be liberated. So the ease of liberation, or the ease of an ion becoming discharged, increases down the series here. So OH, it requires less energy for OH to be liberated than our sulfate. So OH will be given the nod. When this happens, and it's very few things that I ask persons to commit to memory. This is one of them. We will have, this is the ionic half equation for when OH minus ions are liberated. For OH minus ions, aqueous, to give. So we need the arrow here. And this will give us 2 water, which is a liquid, plus oxygen, that's O2 gas, plus 4 electrons. These 4 electrons that are liberated, or these 4 electrons are made available at the anode. They're pulled up at the anode, sucked in at the positive terminal of the power supply or the battery, pushed out at the cathode and at the negative terminal, and then they travel down to the wire. If there's a bulb, the bulb lights up, it goes, they make themselves available at the cathode. They're pushed out at the cathode now. These same electrons that are given up or made available at the anode, these are the same electrons that are going to now be received at the cathode. So at the cathode, our hydrogen or H plus ions are waiting. So we'll have 4H plus, or we could just have H plus, but because we know it's 4 electrons, the same electrons that are lost are the same electrons that are gained. It's a transfer of electron process. So we'll have our H plus ions waiting, and they will accept those 4 electrons, and they will form hydrogen gas. 2 moles of hydrogen gas. So bubbling will be taking place at the cathode. Bubbling will be taking place at the anode as well. And we'd expect twice the amount of bubbling to be taking place at the cathode for, I won't say obvious reasons, but we have 2 moles of gas at the cathode, 1 mole of gas at the anode. Okay, so what we're going to do now to get the balanced equation, we will now combine these 2 half equations that are in blue. Again, our final answer is in red. So when we combine our half equations, this is what we're going to get. We're going to put all that is on the left-hand side together and everything on the right-hand side on the right-hand side together. So on the left-hand side, we'll have 4OH minus aqueous plus 4H plus aqueous plus 4 electrons to give, let's look at what's on the right, starting with the top equation, the top half equation. 2 water, liquid, plus O2 gas, plus 4 electrons, plus H2 gas. And just so things don't look too crowded, let's just clear the sidebar or the side part of the board or our paper. So there we go. So what we'll do now, when we have this, we now cancel out based on electrons. So 4 electrons are on the left. Let's get that back, not there. Right. So we're going to now cross out our electrons. We have 4 electrons on the left, 4 electrons on the right. So we eliminate them, and whatever we're left with is our balanced equation. So the transfer of electrons, 4 electrons on the left, 4 electrons on the right, is just showing you what is happening overall with the whole process. It's a transfer of electron process. When we take out those electrons now, we just show you the net overall balanced equation, if that's even a word. So the final thing now is what we would give as our answer. So, and we're working with what's in red. So this would be 4OH minus aqueous plus 4H plus aqueous to give 2H2O liquid plus O2 gas plus H2 gas. This is what is happening. This is what is happening overall. So this is what our answer would be. And we had what's in red for the earlier part. So that would give us full marks. So that's it. Electrolysis is redox is a transfer of electron process. And electrolysis is pretty much redox applied. So here we go. 6 marks and a total of 15 marks. So if you like this, if you found value here, please give it a thumbs up, share the value with your friends, and if you haven't subscribed, please subscribe so you will not be left out each time new material is added. So subscribe and hit that bell. Thank you for joining Chem with Chem, and as we always say, copper later.